In the 1970s, an astronomer at the Carnegie Institution in Washington, D.C., sat with a set of measurements that did not make any sense and quietly decided to double-check every single one of them before she told anyone. She had been measuring how fast stars orbit around the outer edges of spiral galaxies, expecting, based on the same basic physics that governs how planets orbit our own sun, that stars farther from a galaxy's center should move noticeably slower than stars closer in. Instead, her data showed something that broke that expectation completely. The outer stars were moving just as fast as the inner ones, sometimes faster, a result that should have been physically impossible unless an enormous amount of invisible mass was hiding throughout the galaxy, exerting gravity on everything around it without emitting any detectable light at all. Her name was Vera Rubin, and admitting that finding meant staking her entire career on the existence of something nobody had ever actually seen. Nearly 50 years later, on June 23, 2025, a telescope built in her name and finished 9 years after her death revealed its first images to the world. And it is now spending an entire decade doing exactly what she spent her life fighting to make possible, mapping the invisible material she spent her career trying to prove was actually there. This is the story of that telescope's first images, and the woman whose name it carries and why understanding her own story is the key to understanding exactly what this observatory was actually built to accomplish. Vera Cooper Rubin was born in Philadelphia on July 23, 1928, and by the time she was 10 years old, already sketching the paths of stars from her own bedroom window, her father had helped her build a homemade telescope out of spare parts so she could see farther into the night sky than her own eyes alone could manage. That early fascination never left her, and by the time she graduated from Vassar College in 1948, she was the only astronomy major in her entire graduating class. When she applied to continue her studies at Princeton University, she was denied admission outright, not because of her qualifications, but because Princeton's graduate astronomy program did not accept women at all, a policy that would not change until 1975, nearly 3 decades later. Rubin pursued her graduate work instead at Cornell and then Georgetown University, completing a doctoral thesis in 1954 that argued, controversially for its time, that galaxies were not spread evenly throughout the universe, but instead clumped together in larger structures. A finding many of her colleagues initially dismissed, since the leading cosmological theories of the era assumed a smoother, more uniform distribution of galaxies across space. Decades later, that same clumping phenomenon would become a well-established foundational part of modern cosmology, an early sign of a pattern that would repeat throughout Rubin's entire career. Ideas dismissed or doubted at first, only to be vindicated by the weight of evidence years or decades afterward. The discovery that would eventually define her legacy and eventually earn her the honor of having an entire observatory named after her began to take shape in the 1970s, when Rubin partnered with an instrument maker and astronomer named Kent Ford, who had built a specialized spectrograph sensitive enough to measure the velocities of stars orbiting within distant galaxies with far greater precision than had previously been possible. Working together, Rubin and Ford began systematically measuring what astronomers call rotation curves, essentially plotting exactly how fast stars orbit a galaxy's center at varying distances from that center. Basic physics, the same Newtonian principles that accurately predict how planets orbit our own sun, predicted a clear pattern. Stars closer to a galaxy's dense, massive center should orbit quickly, while stars farther out, in the sparser outer regions, should orbit considerably more slowly, exactly the way Mercury circles our sun far faster than distant Neptune does. When Rubin and Ford actually measured these velocities, starting with the nearby Andromeda galaxy, the results did not match that prediction at all. The rotation curves came back essentially flat, with stars in a galaxy's distant outer regions orbiting at speeds nearly identical to stars much closer to the center, a result that, under standard physics, should only be possible if a substantial amount of additional, entirely invisible mass were distributed throughout the outer regions of these galaxies, extending far beyond the visible disk of stars and exerting exactly enough additional gravity to keep those distant outer stars moving as fast as they were. Ashley Yeager, a science journalist who later wrote a detailed biography of Rubin's life and career, has described exactly how clear this specific evidence turned out to be, noting that the rotation curve plots Rubin and Ford produced were remarkably unambiguous, and that the fact these measurements were captured using ordinary visible light, the exact same kind of light astronomers had been working with for centuries, made the results considerably harder for the broader scientific community to dismiss as some kind of instrumental error or observational mistake. The concept of unseen, gravitationally significant mass in the universe was not entirely new. A Swiss astronomer named Fritz Zwicky had first proposed the idea and coined the term dark matter back in 1933 based on his own observations of galaxy clusters. But Zwicky's evidence had remained largely unconvincing to much of the broader astronomical community for decades. Rubin and Ford's systematic, carefully repeated measurements across numerous different galaxies provided something Zwicky's earlier work never had, an overwhelming, consistent, difficult to dismiss body of direct observational evidence. Rubin herself, by her own account, was famously careful and exacting about her own results, once remarking that she would rather drop dead than have another astronomer discover a mistake in her own work, a level of rigor that ultimately helped her findings withstand the scrutiny they inevitably received. It took years for the broader scientific community to fully accept what Rubin and Ford had found. But by the late 1970s and into the 1980s, the evidence had become impossible to responsibly ignore. Rubin's rotation curve measurements are now widely regarded as providing the first genuinely convincing systematic observational evidence for the existence of dark matter, a discovery that fundamentally reshaped modern cosmology and physics. Scientists now estimate that dark matter, this invisible substance, detectable only through its gravitational effects, makes up roughly 85% of all the matter in the entire universe, meaning the ordinary. Visible matter that makes up stars, planets, and everything we can actually see and touch represents only a small fraction of everything that physically exists. And yet, despite the scale and significance of this discovery, dark matter's actual physical nature, what it is actually made of, remains one of the single biggest unsolved mysteries in all of modern physics, a genuinely open question that Rubin herself spent the rest of her career hoping future generations of scientists, with better instruments than she ever had access to, would eventually manage to answer. Rubin passed away on December the 25th, 2016, at the age of 88, widely regarded by that point as one of the most influential astronomers of her generation, and remembered as much for her scientific rigor as for her lifelong advocacy on behalf of women in science, having faced considerable professional obstacles throughout her own career simply because of her gender, and having spent much of her later life actively mentoring and encouraging younger women entering the field. One of her most frequently quoted remarks captures both her scientific confidence and her broader advocacy in a single sentence. Her observation that there is no problem in science that can be solved by a man that cannot also be solved by a woman. In 2019, 3 years after her death, the National Science Foundation and Department of Energy's joint observatory project under construction in Chile, previously known by the more technical name Large Synoptic Survey Telescope, was formally renamed the Vera C. Rubin Observatory, a fitting tribute considering the facility's central scientific mission, involves precisely the kind of large-scale, systematic mapping of galaxies across the universe that defined Rubin's own career, only now conducted at a scale and level of precision she herself never had the technology to achieve. Nearly 9 years after her death, on June 23, 2025, that observatory finally revealed its first images to the public in an event held at the National Academy of Sciences in Washington, D.C., the same city where Rubin herself had conducted much of her own groundbreaking research decades earlier. The observatory sits atop Cerro Pachon, a mountain in Chile specifically chosen for its extraordinarily dry, dark skies, and its centerpiece is the largest digital camera ever constructed in the history of human technology, a car-sized instrument built at the Department of Energy's SLAC National Accelerator Laboratory, capable of capturing images containing 3,200 megapixels in a single exposure. Zeljko Ivezic, the mission's project scientist, explained to the gathered audience that viewing a single one of these images at full resolution would require 400 separate ultra-high-definition television screens arranged together, covering an area roughly the size of an entire basketball court. One image released that day, built from more than 1,100 individual exposures, contained an estimated 10 million galaxies. A figure mission scientists were careful to note represented only about 1/20% of the roughly 20 billion galaxies the observatory expects to eventually capture across its full planned mission. Beyond the sheer scale of the imagery, the observatory's first 10 hours of test observations had already discovered 2,104 previously unknown asteroids, including 7 near-Earth objects, none of which pose any danger to our planet, an early indication of the sheer discovery rate this instrument was clearly capable of sustaining. Michael Kratsios, director of the White House Office of Science and Technology Policy, addressed the room that day with language that captured the genuine emotional weight many scientists in attendance were feeling, remarking that these first exquisite images reminded everyone present of the true meaning of words like awe and wonder, and the genuine limits of ordinary language to properly describe them. Here is where Rubin's own story and this observatory's actual scientific mission connect most directly, and why her name attached to this specific facility carries considerably more weight than a simple honorary gesture. The Vera C. Rubin Observatory's primary 10-year mission, called the Legacy Survey of Space and Time, involves systematically photographing the entire visible southern sky over and over, roughly every few nights, across a full decade, building what mission scientists describe, without much exaggeration, as the greatest cosmic movie ever made. And one of the central scientific goals driving this entire decade-long effort is directly continuing the exact investigation Rubin herself began with Kent Ford back in the 1970s, except now conducted across billions of galaxies rather than the mere dozens Rubin and Ford were able to study using the observational technology available to them at the time. By tracking, with overwhelming statistical precision, exactly how billions upon billions of galaxies are distributed throughout the observable universe, and exactly how that distribution subtly shifts as the survey continues gathering data year after year, scientists are hoping this observatory will finally provide the kind of comprehensive evidence needed to meaningfully constrain and perhaps finally begin to explain what dark matter and its similarly mysterious cousin, dark energy, actually are. Questions Rubin herself spent her entire career gathering the earliest evidence for, without ever getting the chance to see them fully answered. Following that initial June 2025 unveiling, the observatory entered a careful period of final commissioning and operational testing, continuing to demonstrate its extraordinary discovery capacity throughout the process. During a period of early optimization testing in mid-2025, it identified more than 11,000 previously unknown asteroids in just 6 weeks, a total that would represent more than half of what every other observatory on Earth combined typically discovers across an entire year. Then, on February 24, 2026, the observatory activated its real-time public alert system for the first time, issuing 800,000 individual alerts to astronomers around the world in a single night, each one flagging a specific cosmic event, a supernova, an asteroid, a flaring black hole detected somewhere within its continuous stream of data. Once fully operational, this same system is expected to generate as many as 7 million individual alerts every single night. On June 30th, 2026, the observatory finally began its complete official 10-year survey, now producing a new image roughly every 40 seconds, every clear night, systematically building the very data set that scientists hope will finally deliver answers to the questions Vera Rubin first raised with her own modest but meticulous measurements half a century earlier. It is worth sitting for a moment with the specific, almost poetic symmetry of this entire story. Vera Rubin spent her career fighting simply to be allowed into the field of astronomy at all, denied entry to Princeton's graduate program purely because of her gender, and then spent decades more patiently, rigorously gathering evidence for something nobody could actually see, evidence so exacting and so carefully repeated that the broader scientific community eventually had no reasonable choice but to accept it. She never lived to see the observatory built in her honor, and she never lived to see the specific mystery she helped uncover, the true nature of dark matter, actually solved. But the instrument now carrying her name was purpose-built to continue precisely the investigation she started, scaled up from the handful of galaxies she and Kent Ford were able to painstakingly study by hand. To the tens of billions of galaxies, this observatory will systematically map across an entire decade of continuous observation. So here, laid out honestly rather than framed as an isolated, standalone headline, is why scientists were genuinely, visibly moved when this observatory's first images were finally revealed in June of 2025. It was not simply the unveiling of an impressive new instrument, remarkable as its technical specifications genuinely are. It represented the culmination of nearly 3 decades of careful engineering and planning, deliberately named after a scientist who spent her own career proving that the universe contains far more than what we can actually see with our own eyes, finally providing the tools necessary to potentially answer the exact question she spent her life trying to convince the world was worth asking in the first place. Every one of the billions of galaxies this observatory will eventually catalog across its 10-year mission adds one more data point toward finally understanding the invisible scaffolding of dark matter that Vera Rubin first detected, using nothing more than a specialized spectrograph, a handful of nearby galaxies, and an unwavering insistence on double-checking her own results until she was completely certain they were real. If you want to see what this observatory discovers next, as it continues mapping billions of galaxies over the coming decade, in search of the same invisible material Vera Rubin first identified 50 years ago, subscribe and turn on notifications, because this telescope is only just beginning to answer the questions its namesake spent her entire life asking.